And now, without further ado, we've been looking forward. We've seen a lot about Gaussian splatting, I think, over the last 6 months. We're very lucky to have Aras P with us here today, who's been hands-on experimenting with it in Unity and wrote a series of blogs about Gaussian splatting and ways that we might be able to represent it really efficiently and compress it. Even some ideas for where it might land in a standard. I've been following Aras. I think I've been following your blog. I don't know if it's been 20 years, but I feel like it's almost been 20 years. And I've really loved reading everything that you've written around rendering and software architect. And Aras spent quite a while at Unity, and I believe was employee number 4 there. And then when my colleague Kevin Ring and I were working on our virtual globe book, and I wrote a chapter on rendering engine architecture, Aras was the first person I asked, like, hey, would you review that? Would love your input. And then when we were getting started on glTF, Aras was one of the first people I asked. I said, hey, what do you think about this? So really amazing engineer, really great technical writer, has been sharing his knowledge with the community for so long. So Aras, look, we're pumped to have you here. So over to you.
Oh wow. Yeah, so you hyped it up quite a lot, and I have no idea whether I can deliver. Because I guess as a preemptive warning, I kind of stopped working or looking into Gaussian splatting 2 or 3 months ago, and the space has been moving quite a lot since then. There's been like a new paper every day, or 2 or 3 new papers every day. But anyway, I can talk about something, I guess, at least. And if it's completely boring, then just, I guess, someone shout at me to shut up, and then we can move on to more interesting things. Yeah, so, okay, random things about Gaussian splatting. This isn't going to be about sort of standardization process or most of that. Is just sort of very random. Anyway, so there's multiple ways you can represent 3D objects or scenes or reality or imaginable sort of worlds inside a computer. And one of the ones that pretty much everyone is familiar with is classical meshes, whether these are triangle meshes or just polygon meshes or some sort of subdivided meshes or whatever. You have your vertices, you have your faces, and you put on texture maps and colors and shader effects and whatever into that. This is very sort of easy to understand representation, easy to manipulate in 3D editing programs and so on. And it's been with us since forever. Everyone knows about this, right? Cool. Next up, you could have something like voxels, right? Where you represent your world or your object as basically bricks with some attributes like color, opacity, and stuff like that. The most notable example that at least the kids know is Minecraft, but there's been plenty of similar things before that, and this is a useful representation, especially if you can do voxels in some sort of hierarchical tree structure for various things. Maybe not the scenes in most cases, but for example, people do low frequency effects like a global illumination into voxel structures and stuff like that. Then there's like sign distance fields, which is compared to something like meshes, this is fairly new. It's been only with us in any noticeable way for like, I don't know, 10 or 20 years at this point. And if you look at niche corners of the 3D graphics like demo scene, then for example, all the 4 kilobyte demo scene productions are basically sign distance fields these days. But besides that, they are very compact and easy to describe mathematically. These have very downsides in terms of that it's not immediately clear how to create them out of real world things. It's not clear how to edit them, but some people try to do that, and with various degrees of success. Then there's an area that as you can see, I know nothing about, which is nerves. So my view of that is that you get position and viewing direction, then there's some sort of magic, and then you get a picture out of that, and that's basically neural radiant fields. I would imagine it's some sort of neural net that can, given position and viewing direction, can tell you the pixel color somehow, and then that would mean you need a super giant neural net to actually be able to answer that, and people put that into some sort of hierarchical grid structures or whatever to make them more viable to work in reality. But I know nothing about this. Magic. Then you have very simple things like point clouds, where you represent everything as millions and millions or billions of tiny points. And this is very easy to understand. The primary downside is you need lots and lots and lots of points to represent anything because, well, a point is very, very, very small. And then we have Gaussian Splats, which is an artistic depiction of, programmer art trying to draw some ellipses on screen. And Gaussian Splat is basically blobs in space. It's basically just that. It's nothing else. It's like a blob that has a position, rotation, non-uniform scale, opacity, and view-dependent color. And if you put enough of them into proper positions and rotations and colors, then you can get decently looking scenes out of that. There's literally nothing else. There's no AI, there's no machine learning, there's no sort of, there's no textures. It's just sort of colored positioned blobs in space. And actually, the idea is fairly old. It's literally from 2002 paper where they did exactly the same thing, except back then they didn't have a procedure of how to create and position and color these blobs automatically based on input photos. And these days, due to all the advancements in machine learning, there's like pretty good optimization routines using differentiable rendering and gradient descent optimization to be able to semi-efficiently place millions of these blobs in space. So that's altogether, they approximate the input photos as best as they can. And that is Gaussian Splats. Like, that's it. Now, there's probably one thing that I kind of played around with a while ago, which is that Gaussian Splats take up quite a lot of space. The standard format that everyone uses in the Gaussian Splat community right now is just Stanford PLY format, which is a very simple format for point clouds with custom attributes. And they put all the, a Gaussian Splat is a point cloud with a bunch of extra attributes. So each point, each splat in the standard PLY file that everyone uses is almost 1/4 kilobyte. And you usually need up to 500,000 of these points to decently represent a single object that you can rotate around. And for a decently sized scene, you need 5 million or whatever of these splats. So you're looking at, 100 megabytes file or memory size for a single object, and a gigabyte of memory size for not too large scene in terms of room or a single building sort of site scene, and that is not very small. If you look at the actual data that the typical full Gaussian Splat format contains, this drawing is pretty much to scale, where sort of each little square is a single float, and single float is 4 bytes. So You have your position, color, scale, rotation, alpha for the opacity, and then you have spherical harmonics data, which take up majority of the data size. So basically, 70% of all the data size is spherical harmonics data. There's also normals, 12 bytes for normals that are not used for anything whatsoever. I have no idea why the original paper put in normals in there, even though it doesn't use them at all. And then everyone else continued to put normals in there for no reason whatsoever. So you can just ignore that completely. So looking at this data, basically, if you think about data compression or sort of how to allocate data, in a better way, then almost immediately you could ask whether spherical harmonics, that much data just for spherical harmonics actually makes sense. And as a reminder, spherical harmonics is a way to represent color in a view directional fashion. So in addition to the regular color that sort of the base color of the splat that it has here, which is RGB float for the color, then the rest is sort of the spherical, the view directional effect, additional effect on the color. If you look at the actual scene done with Gaussian splats, so this scene is something that I have captured myself just in my shed, and this scene contains something like 200,000, if I remember correctly, splats. And as you can see, it looks sort of pretty good. In this slide, it's only a photo, so you cannot actually rotate and look at it from various angles. But in the actual Gaussian splat viewer, you can, and it looks pretty okay, right? Now, if you take out all the spherical harmonics completely, then it looks like this, which if I toggle between these, yeah, there is some difference, but even without the actual spherical harmonics, I mean, it's fine. So if you're looking for super easy file savings, then throw away all the spherical harmonics and you're left with 1/4 of the file size immediately, just like that. If you look at the same scene with only the spherical harmonics, then you can see that, yeah, it's basically the shiny, the specular parts that are mostly spherical harmonics things. If you throw all of them away, then the scene looks kind of more diffuse, slightly less specular, and sort of slightly less realistic, less shiny. How much of that effect contributes to the perception of reality is a good question. But as another example, here's another scene that I also sort of made myself, and then I threw in the photos into luma.ai, Gaussian Splats training, whatever service, and then you can download the Gaussian Splat PLY file out of them. The thing is that whenever well, maybe I should preface that with that right now there's basically 2 web services that can create Gaussian splats for you. There's either luma.ai or there's Polycam. And into both you can either upload your own photos or videos, or in case of Luma, they have an app that can do them that can do that for you automatically straight out of your phone. Now, the thing is, if you download a Gaussian splat from Luma, then at least today, what you download has no spherical harmonics in it whatsoever. And if at any point you're wondering why your Gaussian splat that you downloaded from Luma looks slightly worse than what it looks like in Luma's own website or Luma's own app, then that's probably why. Now, the reason that it has no spherical harmonics is a good question. Like, why they don't do that, I don't know. It might be that they are not actually using spherical harmonics in the pipeline, and they are using something else. Anyway, I guess my point is that if file or memory size is a concern, then dropping spherical harmonics, yeah, it loses some realism, but it's not too bad and immediate and easy savings.
Aras,
Yeah.
Aras, there's a question in chat that's related to spherical harmonics. Do you want to take that now, maybe?
Let me read it. Yeah, no. So all the lighting is baked into Splats as it is right now, including the base color. So if you want to remove lighting, then you need to think about what to do with the base color as well. And it's a good question in how to relight splats in general, but if you drop away spherical harmonics, then you lose some of the specular effects that might be due to lighting, might be due to distant lighting or local lighting or local reflections or ambient occlusion or specular occlusion and stuff like that. But the main color is baked into the splat color, and majority of ambient occlusion is baked into that as well. So it's kind of harder than just removing spherical harmonics. Yeah, let me. Right, and in terms of further compression, then I did a couple of blog posts about the ways I tried to compress Gaussian splat assets, and sort of the long story short is that you can compress them up to almost 20 times while keeping some sort of spherical harmonic effects in there by basically quantizing things. And instead of storing the whole set of spherical harmonics for each and every splat, you just sort of do a vector quantization into them and have a dictionary of all the possible spherical harmonics. And per splat, you store just the index into that dictionary. This is an approximation, but it kind of looks pretty good. Then there's other people like PlayCanvas, which is a JavaScript based 3D engine for the web. They do the simple thing. They completely drop spherical harmonics, which is an instant 4 times size savings. And then they do very similar thing where they quantize the rest of the data. And in the final result, they get like 50 times data size reduction. They do lose all this sort of the subtle but nice effects of some specularity. They also have a tool called SuperSplat, which is a web-based Gaussian Splat editor where you can load your PLY files and sort of edit the splats and remove the ones that you don't want and export them back and whatever. And that tool is open source as far as I remember. The other one, which is not a tool as far as I can tell, but more like a recent paper, and I think they released the code fairly recently, which is called Light Gaussian. I haven't looked into it in detail, but they claim about 15 times size reduction by first sort of just optimizing the Gaussian splats in terms of removing the ones that contribute very little and merging some of them in some sort of clever way. And then they represent spherical harmonics in some sort of also vector quantization based method and quantize the rest of the data. Again, sort of probably slightly smarter approach than just very simple quantization. They claim about 15 times size reduction, which is also very similar to the previous slides. They do also claim faster rendering times, though. which I haven't actually verified, but that's what the paper says. And there's probably some more research into that recently, but as I mentioned in the beginning, I'm not actually following that lately. There are people who are following all the Gaussian Splat related research, and they have this GitHub repo with all the papers in there, and they update that every day. And it's still true that every day there is a new paper about Gaussian Splats. Some of the papers have very little to contribute. Some of them are kind of, as always, dubious inventions, but some of them are really, really good. So if you want to know everything that's happening in Gaussian splatting in terms of research and papers, then this is the link that you should check. Good luck reading through 300 papers or so. Okay, now from the compression into some random thoughts about Gaussian splats is that probably using spherical harmonics for the view dependency of the color is not optimal. I guess someone should look into using spherical Gaussians or something like that for these effects. Maybe they would work better. How to make splats react to real-time lighting is a good question. And this is sort of very similar to what's happening with nerves, is that they also capture reality, including the lighting. And relighting that is kind of not trivial in how to do that properly. My impression from reading various papers is that some of them are in the phase that real-time computer graphics was in the late 90s, where, they had things like, oh, we'll just take a texture and multiply the shadow on top of that, which is not the physically correct way of doing, lighting. And their relighting approaches in some cases smell a bit like that, where we have this baked lighting and then we add additional shadows on top of that, which is, okay, maybe it works in some cases, but it's definitely not physically based. There's a reason why movies move to physically based lighting and games have largely moved to, in that it's much more controllable and predictable and works in much larger set of situations. So that's an open area of research, I guess, in how to do that properly. The other thing I've heard people who are playing with Gaussian splats in VR is that implementations, all the implementations so far only sort the splats based on their center position, which means when you're rotating your head around in VR, some of the splats change the order in terms of which one is in front, in terms of which one is behind the other splats. And that is apparently fairly annoying in VR. It's not an issue outside of VR, it's just sort of a very small glitch that you barely notice, but apparently in VR it's a more serious issue. Someone should come up with ways of solving that somehow. I don't know how. The other thing, somewhat related, is that overall sorting of the splats is a bit of a hassle. Splats are just semi-transparent blobs in space, and with any semi-transparent things, typical way of rendering them is that you need to sort them front to back or back to front or whatever, right? And for a decently sized scene, you have like 5 million splats, which means that every frame you need to sort 5 million things. Now, of course, you can do the sorting on the GPU, and that takes like 1 or 2 milliseconds, which is not the end of the world, but especially in VR, 1 or 2 milliseconds is a non-trivial part of your frame budget. And so some people have played around with the idea of not sorting at all, and instead of using just stochastic transparency techniques that then don't require sorting, but they introduce some sort of noise into the resulting image. I haven't followed closely whether anyone got really good results out of that, but this is an area that's definitely someone should look into that, or invent a way of not sorting everything, at least every frame, and some sort of incremental sorting, or I don't know. The other things probably finally somewhat related to this whole forum is that whether a file or interchange format for Gaussian splats should be developed right now. And I don't know the answer to this question. There has been some online discussion among open source Gaussian Splat, mostly JavaScript and WebGL based viewers about that they should settle onto some file format that is smaller than the full PLY, because especially for web cases, the file size actually matter. But the discussion, as far as I know, has kind of fizzled out with no clear answers. It might be that it's too early to standardize that because, yeah, there's a new paper coming every day, and maybe it needs at least half a year more to see where all of this is going. Because even though the core idea of Gaussian splats is literally 20 years old, it has been largely forgotten until this past summer, where people have resurrected that idea, and now everyone's kind of, whoa, new thing. Anyway, and I think that's it for me. I can answer any questions that you might have about this, but yeah, I don't have anything else from my side to say, I think. So I'm gonna stop the screen share.
Aras, that was really good. I have a pile of questions, but let's go to everyone else first. Who has questions? So Aras, maybe if I could then kick things off. I know you were talking a bit about at runtime, a lot of folks today are sorting back to front. You can sort on the GPU. Could you even walk us through a little bit more of what the rendering pipe looks like? Like, are they using discard and the fragment shader in order to make the splat?
Yeah. So as far as I can tell, there's at least two possible approaches. The actual Gaussian splatting paper, they implemented the rendering pipeline completely with CUDA, which means they are not using any of the fixed function pipeline of the GPU. They do one very big sort of the whole scene, again using CUDA's libraries, because CUDA helpfully provides radix sort and everything that you might need. And then they do a tile-based rasterizer inside CUDA. Now, a tile-based rasterizer makes sense for this because it saves a lot of bandwidth in terms of blending the splats into the frame buffer. It's kind of hard to do, I guess, without CUDA. It's a bit of a hassle because with CUDA, what's much easier than in regular 3D graphics APIs is that you, for example, can allocate GPU memory from the GPU code itself. And when you're sorting the splats and allocating them into screen space tiles, then you have no idea how many splats, how much storage you might need per tile. Depending on your view direction. If you're completely zoomed out, it might be that all the 6 million splats are within one tile and all the other tiles are empty. Yep. So you need to be very conservative with buffer size allocations and whatever. So the tile-based rasterizer uses quite a lot of memory, even with CUDA. I think they have for 1.5 gigabyte splat file, they need an extra 3 or 4 gigabytes of VRAM for the tile buffers and sorting buffers and whatever, right? Which is I mean, for a paper, it's completely fine, and for a high-end GPU, it's completely fine. But it's not exactly cheap. The other much simpler to implement approach, slightly less performant, is just to render splats as screen space of rectangles, and then you alpha blend them together using just GPU blending. And the splat, I mean, they're named Gaussian because they kind of fade out towards the edge, but it's just a blob that fades out. It's sort of very, very simple. So you do alpha blending. Whether discarding pixels outside of the splat ellipse shape helps or not depends on the GPU architecture mostly. But you just kind of blend the splats together, and then obviously you're mostly limited by memory bandwidth because the GPU has to just blend many things. So on GPU architectures that are inherently tied, like most mobile architectures or like Apple GPUs on desktops, they're probably less memory bandwidth bound because they internally have tile rasterizer. But basically that's it. There's like literally nothing very complex or clever. When I was implementing this Gaussian splat rendering inside of Unity, the most complex thing was actually finding a decently good GPU sorting routine, which is surprisingly hard to find outside of CUDA. Everyone writes their own Bitonic sort as an exercise, but Bitonic sort, while it's parallel, it's nowhere near being the best sorting algorithm on the GPU.
Cool. Did you use a radix sort, or what did you use in your implementation?
I took AMD Fidelity FX radix sort, and I ported that to Unity, which was fairly simple. And that's what it is right now inside the Unity Gaussian splatting GitHub repo. Someone else very recently contributed the somewhat improved radix sort that is kind of based on NVIDIA's one sweep radix sort paper, which I think it does one less pass over memory, something like that, using some clever things that are beyond my understanding. But even radix sort, you can do it in different ways, and this one seems to be slightly faster. I haven't merged that in yet because I didn't test that on AMD GPUs.
Cool. Other questions for Ross? All right, Russ, if I could ask another question then. So you mentioned that just removing the spherical harmonics can reduce the size by 75%. And then for diffuse scenes, that's probably, that might be okay. Does it also have a big impact on the runtime performance, just given, as you were talking about, how much memory bound things could be to the frame buffer?
Much less than I thought it would be. Just skipping the spherical harmonics calculations, I mean, it saves you some amount of reading the spherical harmonic data and doing some amount of math, but that math is only done, once per splat. So, conceptually, in a vertex shade or in a whatever.
I see.
So it doesn't save you any of the per pixel bandwidth at all.
Gotcha. Cool. Other questions? Neil.
Hey, Aras, thank you. That was an awesome presentation. I think I agree. It's moving too fast, probably, to jump in with both feet to standardization on a file format. But thank you for that link. I've been reading the link in GitHub around starting to think about standardizing a file format, and there's a lot of discussion there about glTF2 and even KTX. So recognizing it might be too soon to finalize anything, is there anything that the 3D formats working group at Kronos can do to help prepare the landing strip mainly. Perhaps answering any questions around logistics on doing glTF extensions or KTX extensions, so there's no confusion around that.
As far as I can tell, some of the people in that discussion on GitHub were already people that talked on this forum previously, like from the Needle Tools engine, and that have done some glTF extensions, and they're sort of familiar with how it's done and everything. So I don't think anything extra is needed. From my understanding, extending glTF with, say, ability to store some Gaussian splat data is conceptually trivial. It's just a point cloud with more vertex attributes. Like, that's it, right? Just someone should come up with the hardest part in how to name the attributes. Naming is bad. But I think mostly it's just people waiting for the research to settle down and sort of in a month, an awesome new invention that, I don't know, makes Gaussian splats better while taking up much less space.
I agree. No, the discussion on that thread seemed very well informed. Yes, but if there's anything additional we can do to help, just let us know. I'm certainly going to circulate that thread inside the 3D formats working group so they're aware, so you can get more engagement, perhaps. Yeah.
Other questions? So another question for me. So 2 weeks ago on the call, we had some folks from Adobe on talking about Nurse and a little bit about Gaussian Splats. And I think there's some discussion with the group around even beyond spherical harmonics that MLPs, these multilayer perceptrons, may be used. That's not an area I know about, and there's probably other folks on this call that could chime in. But have you heard of this, or have you looked at this at all?
I've heard of people trying to take the idea of Gaussian splats where they are basically a point cloud in space, a fancy point cloud in space, and to represent the view-dependent effects using, like using a tiny neural net basically inside a splat or inside a chunk of splats or something like that. I've sort of seen some paper titles. I haven't read them, but as I mentioned, there's a new paper every day, and I stopped following that area some months ago. So not an expert at this point.
Aras, maybe another question for you is, so a lot of folks on the call here are, they're involved in glTF or involved in USD or just big users of those formats. Did you have any requests for us or input? Because I know you've been dealing, for example, a lot with Blender recently, if I remember.
Well, I mean, this would be nothing related to Gaussian splats at all, but my personal sort of thing is that I was wondering why USD is well, it's not a file format. Why USD doesn't have a spec? Yet a lot of people are busy building their futures on USD, which to me, it's kind of weird to build your own pipeline on something that doesn't have a spec. Didn't we learn the lesson from FBX?
I think we have good news on this front, actually. Fair question. I don't know if Nick or Guy would want to chime in.
I would say that more than one group is looking at that. I don't know of anything that I could point to as anything that anyone could look at. And if I was personally going to have a look at trying something out, I personally would start with Aras's post that he linked earlier.
Oh, I'm sorry, Nick. This is just USD in general.
With respect to Gaussian Splats.
Gaussian
yeah,
Splats
just
or
in-
USD in general?
I think.
Yes,
Aras,
I
did
am
you
saying
mean-
that there's nothing out there that you can look at right now. There's people who are working on it, but haven't showed their work aside from mentioning that they're doing it. And I was just starting to say that I would have used, if I was going to do it myself, I would start with the information Ross posted on that GitHub issue that he had in his presentation, because the information on that thread is solid gold. But in terms of something that exists today, I can't point to anything.
So Nick, I mean, do you want to, I can grab it too, but do you want to put the post in the blog post about the timeline for core spec? I mean, that's really the first big piece we have. And then I think that there's been discussion steering committee. I'm on the steering committee, Aras, for AOUSD. There's been discussion about kind of an industrial or a interest group. So not a working group. Working groups in AOUSD create the specifications, but we have this concept of an interest group where new things can be discussed and then potentially birth working groups to work on that. And I can imagine that creating an interest group at some point to discuss, nerves, Gaussian splats, sort of new technologies and where those should fit into what we're building in specs would probably be the best course at this point.
What's an AOUSD?
Alliance for Open USD. That's the standardization body now for USD. Sorry.
So Russ, I think the kind of punchline answer to your question is that there are folks working on a specification for USD.
Okay, good. Cool.
Cool. Other questions? Okay, well, Aras, thank you for your presentation and